this is just review. Let's go back over like redox reactions. One thing gets oxidized, one thing gets reduced. That's what oxidation and reduction mean. Make sure you remember that. Half reactions, if you remember, we wrote one half reaction out of like this reaction between permanganate and iron. The permanganate goes from a +7 state over to manganese over here, which is a +2. So it actually gains 5 electrons. So we call that reduction. And of course the iron goes from a 2 to a 3, so we call that oxidation. So it's always one thing losing electrons, another thing gaining electrons. A couple little tips that we need to know just so that tomorrow we can actually come in here and practice this stuff a little bit. There's something called a cell potential, and you may have heard it called electric potential, or you may have heard it called volts before. What forces the electrons along. Potential is always measured in volts. And get down in your notes that a volt is a joule per coulomb. And a coulomb is a certain amount of charge. This is just going to help your stoichiometry go a little bit better. So get down that potential is volts, and it's measured in joules divided by coulombs, J/C. An amp is how much electricity is flowing, and it's equal to a coulomb per second. I means amperes. I don't know why. I is current, or amperes, is equal to Q, which is the charge. I know. Q is coulombs per second. So Q to the T. A volt is joules per coulomb, and amp is Q over T. I always think of it this way. Potential is how fast are the electrons moving. Amps are how many electrons are moving. This is put your finger over the end of a hose, and potential is how fast does the water squirt out. You have a little bit of water squirting out very, very fast. I like to think of an amp as being how fat is that pipe. Okay, so you can have a really skinny pipe with lots of water going really, really fast, or it seems like it. But in reality, it's such a thin pipe, not very much water is going through. That's called voltage. And amps is how big a pipe is it? Is it a little like a 1/4-inch pipe, or is it a 7-foot pipe? How much electrons are flowing across it? So as an example, in a wall, it's 120 volts. In a car, it's 12 volts. In a house, like when you plug something in, that may be 10 amps. That's a lot of amps. Whereas in a car, it could be 75 amps, enough to start the car. The wire in a car is way thicker to allow all those electrons to flow, and the wire in your house is thinner. Usually the less number of amps it has, the smaller the cable is. That's why Christmas tree lights are so thin. All right, enough talk. A galvanic cell is one in which it's a battery where you take chemical energy and you turn it into electrical energy. And it always happens, right? It has a negative delta G because it's a battery. It just works. The E is the electrode potential. Now that 0 up there, that means at standard conditions, and we'll get to that more so in practice. But just get that it's always positive. The E of the cell is always positive. That's a galvanic cell. That's where chemical energy gets turned into electricity. The opposite of that is an electrolytic cell. This is where you recharge a battery. So this is where electrical energy gets turned into chemical energy. It always has a positive delta G, meaning batteries don't charge themselves. Hello, that kind of makes sense. And this electrode potential, the cell potential, the number of volts, is always negative. You guys need to know some basic definitions of anode and cathode. If you can remember that oxidation, taking electrons away, always occurs at an anode, and reduction, gaining electrons, always occurs at the cathode. And if you can remember red cat and anox, reduction at the cathode, at the anode is where oxidation happens. So we can look here, anode, what happens at the anode, anox, so that's where oxidation happens. So electrons are being lost, and they travel up this and across the wire and down to here. And over here, this is the cathode. This is where reduction takes place because that's where something is gaining electrons. And you might be saying, well, is this electrolytic or galvanic cell? Assuming I can say electrolytic. And a galvanic cell is one that does not require an external power source. This is a galvanic cell. Electrolytic would mean you'd have to have some power source in here, something that's recharging the battery. Here's another cell. Again, we have an anode and a cathode. The electron flow, it always goes from the anode over to the cathode. Even in this one, the electron flow goes from the anode to the cathode. Just something to keep in mind. So you can get this in your notes. We have the same cell, but it's two different types. Right here, this is a voltmeter. This is not a power source. This is just something that measures the volts coming off. So this is a galvanic cell, because the galvanic cell is actually producing electrons all on its own, and we can measure the voltage. Here, this is an electrolytic cell. This is where we're actually taking the electrons and we're reversing the flow of electrons. And because we can overcome that, we can actually recharge the electrons. Here you might be saying, well, I wonder what's happening here. Well, the zinc is going to be giving up electrons. So that zinc solid is going to be turning into zinc plus 2. So this thing right here, this will actually go away over time. And over here, this copper and the copper ions in solution, those copper ions will actually be gaining electrons. And when they gain electrons, they'll form on the outside. So if you were to actually look at this, the zinc electrode over here will actually get smaller, and the copper and cathode over here will actually get bigger over time. Now, if you want to redo that, if you want to get it back to the state it was before, you just have to apply an electrical force and make those electrons travel back originally where they were. Now, I haven't mentioned this thing here in the middle. This is called a salt bridge. And this is necessary because if all the electrons traveled from the pink side over to the blue side, what would happen is this pink side would become very, very positive because it's losing all the electrons. This side would become very, very negative. The whole thing would lock up because the charge potential, positive and negative, become way too much. So this salt bridge right here, this is a way for those ions to travel back and forth. So this side doesn't get too positive, this side doesn't get too negative. It kind of evens it out. And that's necessary for any cell to function. If you didn't have this, yes, you'd have electrons would flow, but not for very long. These are the kind of problems you're going to see in electrochemistry. So I want you guys to go ahead. You can be looking over this, delta G, voltage, make a list of these. And I'll show you how to do each one of these. They are electrode potentials measured in volts at standard conditions, and we'll use these to actually solve problems. They are just examples of electrode potentials. When things lose electrons, how many volts are given off. This is what you're going to do anytime you have to do a cell potential problem. We have to find the standard potential. That's what this means right here for the reaction. Split up your half reactions. Now, one of these doesn't look like it is up above, right? There's iron 3 turning into iron 2. Iron 3 turning iron 2. That one's okay. This copper one right here, that's copper. It's on the wrong side of the arrow. There's copper 2. It's on the wrong side of the arrow. So what we need to do is we need to worry about flipping one of these. So we have to flip one of them. Obviously, we have to flip the copper one to make it right. And the rule is that when we flip it, you turn this positive 0.34 to negative 0.34. So all you have to do is figure out which one do you want to flip it, and when you do that, you flip the sign, and then you just add them together. So this is 0.77 and negative 0.34, and you get 0.43. This is positive 0.43 volts. That's all you have to do. Look at the reaction, write down your half reactions, figure out which one needs to be flipped.